So last time we ended on a cliffhanger. I drew for you this page curve. We had two lines. We had the entanglement entropy. This is T. And we had the black hole entropy. And the statement that we made was that it's even though we set up the calculation within the low energy effective theory, and so therefore everything should be able to be captured by the low energy effective theory, we somehow are unable to reproduce this red curve in the low energy approximation, which is bizarre because everything that we did was within that approximation, and so you know, why are we unable to reproduce this curve? What is the mistake that we made that makes us unable to calculate the red curve within the low energy approximation, even though every part of the calculation was within that approximation? So just a reminder, the statement that we made last time is that in the low energy approximation, we're able to calculate this yellow curve, and the yellow curve is the wrong answer. The correct answer is the red curve. Okay? Well, it's what's consistent with unitarity. So if the yellow curve is true, then you would have a time evolution that would take you from a pure state. So you have to imagine the following scenario. You start with a gas of stuff, maybe some galactic disk, and you prepare it in such a way that eventually it collapses and forms a black hole. So, okay, so your gas is in a pure state, a pure quantum state. And you know, the entanglement entropy of all of your initial state is 0 because you're in some pure state. So that's here. You let it collapse and form a black hole, and then all of a sudden this thing starts to populate radiation thermally, the characteristic temperature of the black hole. And because you now only have access to the stuff outside the black hole, you start building up entanglement between the stuff outside and the stuff inside. And that's why this curve increases, the entanglement entropy increases. But at some point, you know, well, what happens is that the black hole, as it starts to emit this radiation, it's shrinking. So the black hole's entropy in you know, the semi-classical calculation, A over 4G, is decreasing. But the entanglement entropy you calculate using the effective picture, where you have a horizon and you split modes across the horizon, you do this Rindler calculation. That thing is always thermal, so the entanglement entropy you calculate that way is always increasing. But at some point, the black hole is gone. It's just completely disappeared, so there's no inside anymore. So at some point, you're left with a state whose entanglement entropy is non-zero, even though you started with a state whose entanglement entropy was 0. There's nothing left to be entangled with. And the only way to make that consistent with time evolution is if your time evolution is not unitary. Unitary time evolution doesn't achieve this. You can't get that from unitary time evolution. So if this curve were correct, then we would say time evolution is not unitary, and that's probably the last thing that we expect. That would be a terrible violation. That would mean that, you know, standard experimental apparatus is not a useful thing because we can't predict. There's no way to predict. You get non-conservation of probability in that scenario. So that would be bad. So Low energy approximation gives this. Unitarity, the unitary expectation, gives the red curve. And as I emphasized last time, it's very difficult or nearly impossible to get this red curve and stay in the low energy approximation. The low energy approximation assumes that we can trust semi-classical gravity at all steps. We engineered our slices, our Cauchy slices, so that that approximation should be valid at all times. That's why we went through this exercise of saying, okay, the 3 curvature is always going to be small, the 4 curvature is always going to be small, the slices always stay away from the vicinity of the singularity. You know, we engineer it in this way so that it's always some very weakly curved slice, and therefore the low energy approximation should be valid. And nevertheless, we still derived a contradiction. Something is weird. The picture of this horizon, this Rindler horizon that we get from the equivalence principle, leads you to calculate this curve, the yellow curve. And that's wrong. It's wrong because it violates unitarity. And then I left with the open question of what mistake did we make? And I waited for you guys to propose an answer. You know, one potential place where we weren't being exactly precise with our calculations. And I don't think I heard a satisfactory answer. Unless you guys think there was a satisfactory answer that was said. No?
What I was thinking was maybe that as the black hole, after the black hole cracked, you know, that Cauchy slice wasn't like there wasn't enough room between the singularity and the horizon for you to define it without being curved.
That's good. That's a good point. So indeed, what we showed that was that over here, the explanation that I gave was for the end of the evolution. The statement that you know, if you want to purify the state at the very end, then the modes cannot. There has to be this type of structure to the state. That basically, you need a tensor product structure between inside and outside, and that's in contradiction with Rindler calculation, which shows that it's not. You have some mixed state between inside and outside. So that's a very valid statement that, well, how can we trust that picture at the very end when the black hole is very small, right? So the point to make with that is that, well, here, so this time we usually call the page time. That's when the growth of the entanglement entropy starts to turn around, and this is when the black hole is about half of its mass. So we have evaporated about a half of the black hole mass. And if you start with a very big black hole and you shrink it down to half its size, still very big. And the switch around is also impossible to get in the low energy approximation. And so the problem really starts here. So the like technical argument I made was indeed for here. But the problem is here. We can't even get the turnaround. Because the turnaround would mean a violation of this picture that you have entangled state between inside and outside. And this turnaround has to happen when the black hole is still big.
Would this imply that gravity problems will have UBI thing?
A little bit. So there are two things that are important to remember. So one is that, yeah, so there are 2 points that I want to make now. And one of them has to do with your statement. It's not really that the gravity path integral has UV-IR mixing. It's that even when you try to work in the low energy approximation, to get to this point, you need to have shed a huge number of particles. So you're in some state with high occupation number. And even in regular quantum field theory, states with high occupation number, so for example, if you worked in QED and you tried to compute a tree-level graph with n external particles, and just try to work in the tree-level approximation, you would find that you can't control this calculation. A large number of external particles, even at tree level. It's very hard to control this calculation. That's why when we do QFT, we only work with like 2 to 2 scattering, 2 to 3 scattering. When you have large numbers of external particles, you start to run into problems with, how do you compute? And something like that is happening here. You're in some high occupation number state, even though it looks like you should be able to trust the low energy EFT. That's often not the case. So that's point number 1. But point number 2 is even more fundamental. So I'm going to build up point number 2 slowly, but I just want to check: are there any questions about this at this stage? About what I said?
Question about these curves, Hamiltonian curve. So how is this specific for black hole? Simply in contrast with any other quantum system, for example, maybe like a model with fermion that XYK or some other thing, or just some simple spin system.
I mean, yeah. So a curve like this it should never be possible to have a time evolution where you start in some pure state and end up in a mixed state, even in some fermion system that you build in the lab. So at the same time, like making some like big ball of like energetic stuff in some process and then watching the entanglement entropy grow. I mean, you should. Yeah, I don't know how to engineer such an experiment where you get a switchback curve like this in some tabletop setup, but I mean, I think it should look like that if you can engineer it.
Yeah, let me reflect what's the Salad class system? There's other things with it. There's something more general than just about black hole.
Oh, that's a good question. Yeah, that's a good question. I think that we'll do an example at the end. I think that in general, any Lorentz invariant QFT, local Lorentz invariant QFT, should have something like this. So I think it's pretty general. I don't know what like. I think also if you have a lattice system that in the continuum gives a local Lorentz invariant QFT, you should be able to derive something like this. I'll explain that statement towards the end. So I think it's pretty general. I don't know if there are like any particular universality classes that I can say. Like for example, if you have like a 2-qubit system, can you derive a page curve? But I think if you have a large number of degrees of freedom and somehow some notion of locality that emerges in at long distances, then you can. Exactly. What's the relation with the black? Well, we're just formulating the black hole puzzle, and then we're trying to think about what went wrong in the calculation. It's not just like, it would be bad if you had this kind of curve in general. My statement is that, the whole point of this class is to introduce the black hole information paradox and say, what it is precisely. But indeed, if you had such a curve like, like this, in any quantum system, it's not special that, you know, for black holes that this would be bad. Interior quanta being replaced? Yeah, I mean, well, yeah, that's correct. I mean, yeah, the interior is completely disconnected from the exterior. So yeah, you're just building up a bunch of entanglement, and your statement is that there's no process by which, you know, you could purify because that. But I think that that's, you know, that's not quite correct. I think that I mean, this whole like Hawking evaporation process is the black hole releasing some of its interior mass. So yeah, I think the main point is that the structure of the state has to change from being in this kind of like entangled state between inside and outside at some point early on. Non-locality. Well, it's derived using locality and just regular rules of quantum field theory. So I don't think that that plays any role. Okay, so we're gonna get to point 2. So this is a very subtle point that I was hoping somebody would mention, but it's okay that nobody did. By the way, I need to make a statement for the YouTube fans out there. This is the last lecture. If you enjoyed it, please give us a like and a subscribe. Okay, so last time I introduced this property of states. So remember last time we talked about some 2-qubit system, and I defined a state psi on 2 qubits, which looked like this. Remember this? We had this 2-qubit system. We defined the state psi, and we contrasted it with this other state chi, which was just down, down. And remember we said that the difference between these two states is that this state psi, you could generate all of H with local operations in X. So local. So we made the statement that you could act only in one subsystem, so in the subsystem X, and generate all of the Hilbert space. And we contrasted that with the state chi, where that wasn't possible. Right? You guys remember that? Okay. So both of these are pure states, but the state that you get when you trace out one of the subsystems, Y or X, differs. In this state, you would have no entanglement, and here you would have entanglement. But the important thing that I want to bring up right now is that this state psi is an example of what we call a cyclic state. So a cyclic state is a state that you have on a Hilbert space where acting on some subsystem lets you generate the whole Hilbert space. So for example, if x and y are both k-dimensional, then the generalization of the state psi would be something like this. And these square root of pi's are the probabilities of being in any of these mixtures. So this would be something like a cyclic state, up to phases. Okay, so this would be cyclic. We say with respect to operators in, and when I say in, I mean acting on x or y, if and only if none of the pi equals 0. If any one of these pi's is 0, then your state is not cyclic. Okay? So I want you to remember this statement about states. You can have states that are cyclic, and you can have states that are not. Cyclic state is one where if you have a subsystem, you act only on the subsystem, you can nevertheless generate the Hilbert space. Okay? All right. But this was for a 2-qubit system, and this is for a 2-qubit K-state system. But we were working in QFT, remember? So now I have to tell you how this works in QFT.
Why do you find to stay in this form? I think it's only any other type of like veil pair.
Oh no, it was just it was just to give an example. Okay, so we derived this Rindler state in the low energy UFT of flat space QFT, Minkowski space QFT. So I'm going to remind you a little bit about things that maybe you've learned, maybe you haven't in Minkowski QFT that you might have taken for granted. Okay, so in QFT in flat space, we're interested in the Hilbert space built out of acting with creation and annihilation operators on the vacuum. Remember? Okay, so what is the vacuum? So usually in flat space, in the continuum, we're interested in Lorentz invariant QFTs. And Lorentz invariance implies that translations of my vacuum is annihilated under translations. That's the statement that the vacuum is invariant under translations. Because if you don't remember why that is, it's because the finite generator would be something like e to the IP mu acting on the vacuum. And if this is invariant, then you should get the vacuum back. And you just expand this guy, And you see you'll get powers of p, and it's sufficient for the generator of p acting on the vacuum to annihilate it so that this is true. Okay. And besides that, we're interested in local quantum fields. Local quantum fields are operators that act on Hilbert space. So we have fields labeled by a point in spacetime, x mu. And Lorentz invariance, moreover, implies that the commutators of any two fields is equal to 0 if x mu minus y mu is space-like. Okay, so this is basic construction, and this phi will be a scalar field, but you can generalize this to fields with spin. Now, the Hilbert space of my local quantum field theory, remember, is the span of both this vacuum state and any product of these local operators acting on the vacuum for all n. And remember, we quantize on a Cauchy slice, so let's pick one. So we're going to make all our ti equals 0, so that's xi 0, and xi r3. So this is our Hilbert space. This is the span of our Hilbert space. Now, why am I going through this whole procedure? Well, one thing that is important to know about QFT in flat space is kind of a surprising fact. Let me know when I can erase this. Yeah? So, yeah, I'm thinking about continuum theory, and I'm only thinking about the perturbative Hilbert space. Yeah. Yeah, this is, for the experts out there, this is how you construct the GNS Hilbert space in algebraic quantum field theory. Okay, so the surprising fact which is a result of Ray and Schlieder, from 1961, is that the vacuum is cyclic with respect to subregions of the Cauchy slice. All right, so if you're awake, can somebody tell me what that means? You remember what cyclic means? All of the Hilbert space, that's right. Okay, so, and let me say bounded subregions. So let me draw my Cauchy slice. Let me draw a bounded subregion. So this Cauchy slice extends to infinity, right? In all directions. And I act with local operators in this region. And I can generate the entire Hilbert space. So what does that mean? Yeah, so that means that just like we were saying before, this red region is entangled with everything outside of this region. But what's more interesting is that this is true for any subregion, any bounded subregion.
So you fix the subregion and the vacuum gets the frequency that operating on and off this subregion.
Correct, correct. So so that means, let me redraw this picture slightly better for what I'm going to do. I'm going to draw it bigger. So if I act in this local region, I can generate the entire Hilbert space. What's even more surprising is that I can make that region smaller, and I can still generate the whole Hilbert space. So the vacuum, so let's say R prime, this is R. If R prime is contained in R, then the vacuum is still cyclic with respect to R prime, and it's also cyclic with respect to some completely causally disconnected space-like separated subregion, R triple prime. Okay, so these two things. One is R prime has fewer operators than R, technically, right? It's a smaller subregion. So I can still generate the Hilbert space if I restrict to fewer operators, right? And you can imagine doing this procedure sequentially, making it smaller and smaller until you're only left with a couple of lattice sites, and you can only act locally with lattice sites on particular. You can still generate the entire Hilbert space. So what do you think that tells us?
Does the theorem not like specifically assume you have an infinite number of operators? So you, like there's a finite matrix.
It's yeah, a little bit, but still. So I want you to imagine what this means. What this means is that in analogy with our state psi, the vacuum O I can write as some formal sum over I inside R and I outside R. And there's a square root of pi here. There are an infinite number of operators. So what does this tell you? Say I traced out the outside. How much entanglement would there be between inside and outside? I want to hear it. Yeah, the entanglement entropy is infinite. S inside. Okay, technically nothing's infinite, so this is, you never write this. The more precise statement is that entanglement entropies are UV divergent quantities in quantum field theory. Local quantum field theory, when we talk about entanglement entropies, they're UV divergent. So we have to be careful. So when I draw this plot for you, you know, here is the entanglement entropy increasing with time. First, the one thing I hoped to hear last time was, wait a second, that's a UV divergent quantity. What the hell are you plotting? So So we haven't been fully precise yet. So the correct statement is that this is equal. There's some way to regulate this. You can pick a way. You can cut off modes at some length scale. But if you do this calculation in a number of ways, you'll find that this is equal to area of R divided by some UV cutoff scale. So UV divergent quantity, but it scales with the area of R. There's another point that I want to bring up is that, so roughly speaking, the vacuum state looks like this. So the vacuum state is cyclic with respect to inside and outside of any subregion. But all states at short distances look like the vacuum. If you zoom in close enough, this is because you generate the Hilbert space by acting with local operators. You can pick some region where there's no local operators and you zoom into it. So every state at short distances looks like the vacuum. So there is no analog of the state chi. There is no analog of a non-cyclic state in QFT. All states are cyclic in QFT.
Again, so example to state, let's take vacuum and let's act on it with operators local in R.
Yeah.
Right. Now you say so the same state can be generated with operators acting only in R.
Yeah. Yeah. Why?
Well, because you have to also be how. I don't know.
The statement of the theorem is that you can compute the difference of the states, and they become their overlap goes to 1 in some.
But if they not even like connected.
It's the same as this chi state, right? Remember, or the psi state. Remember the psi state, I can act on just X, on the X subspace, and generate all of the Hilbert space. It's the exact analog. I've never acted on Y. I separated my degrees of freedom into two subsystems, X and Y, and I act only on X, and I generate the whole Hilbert space. In local quantum field theory, you have to be careful. You have to use, real analysis and all that stuff. And so, that there's a statement that these, the Hilbert space is dense in R. So you have to consider, real Cauchy sequences of operators and like show that the overlap between any two states is bounded, epsilons and deltas. You know what I mean? But this is a It's super, yes, exactly. It's super entangled. It's super entangled. The entanglement entropy, that's why it's a UV divergent quantity. That's the entire statement of the theorem.
Regarding like math behavior of the since I assume it's there like design.
I think it's true also for fermions.
What if you have a CFT? What is that? Happens with area time?
It's the same.
It doesn't be kind of conform symmetry with that.
Well, you break the symmetry by introducing a subregion.
Oh,
yeah, you have to define a region first, and then you ask what is the entanglement entropy. So that splits the system. Right? You have to define the region first that you're acting with local operators, and then you trace out everything outside of it. And then you ask what is the entanglement entropy. It's very subtle. Very subtle. So I'm not going to get into that. Yeah, the UV part is the same, but there are other parts that you have to be careful with. Yeah, it's hard to define how you do the splitting precisely. That's another point that I'm going to get into with respect to gravity.
So this is for vacuum, and if you work in the constant thermal state, then it would be volume. So, right? So
No, it has to do with the fact that at short distances, everything looks like the vacuum, even a thermal state. This is the first UV divergent piece. There are subleading pieces that distinguish between the states, but the entanglement entropy and yeah, maybe I think okay, maybe maybe my statement is incorrect. Maybe my statement is only for because the thermal state is an exponential operator away, so it's very far from the. So if you're just working in the perturbative Hilbert space, then this is true, and maybe thermal states are not in the perturbative Hilbert space. I have to check. Okay, so very important that when we talk about black hole entropy, so we have a black hole. So we have S black hole divided by a black hole. This is 1 over 4g. This number is 1.4 times 10 to the 69 bits per square meter. So it's huge. It's a humongous number of bits per square meter, but it's not infinite. It's not UV divergent. So we often take the fact that this is a finite quantity for granted, and we need to think very carefully about what that means. Okay. Yeah, so there's one second point that I want to mention, which has to do with this gauge theory question that Chaucorn asked. This is huge, but not infinite.
Yeah, but see on top of the 8 part in the QMUL product.
All things conspiring to make you big. All right. So there's another point that now in gauge theory, it's much more complicated because of the existence of non-local operators. So what you need to take care of? So so in gauge theory, you have to worry about yeah. So you have to work in subspaces of fixed charge, and when you do that, you can define a splitting. People care very much about how to like make this precise. I can point you to papers by, for example, Will Donnelly. But there are ambiguities in the answer depending on how you do the splitting. This is why it's subtle. In particular, if you have Yang-Mills theory and not just U1, there are these dim R terms that in one way of doing the splitting, you get this finite piece that contributes, whereas in other ways of calculating it, you don't. For example, if you do the Euclidean path. I think, yeah, some people believe the splitting can be done. I'm not an expert on it, but I think that there are still these subtleties, and there's still like this confusion in the literature. But I think, yeah, there's a belief that there is a notion of entanglement entropy that you can well define in some way, or at least. The full perturbative Hilbert space by, yeah, by I think, yeah.
Maybe know the subtlety will be how many factors, or how many ways you are putting the local charge for the non-local game theory.
Right.
But for the scalar field.
Yeah. Yeah. For the scalar field, this is old stuff. Everybody, I think, understands. Yeah.
I guess the game theory part probably will be work out once people know some property of the homology, that kind of things. For example, if there's
But I mean, I think there are subtleties even when there's no topology. So if you just work in flat space, or Euclidean flat space, there's still issues. Like I think that you don't have to go very far and work in topologically interesting or non-trivial manifolds to see the confusion. It just has to do with the fact that your operators are no longer local only. Okay, so point 2 is that when I set up this problem for you, I defined these nice slices, right? And we talked about, so here's our black hole. It evaporates. So what did we do? We had the inside of the black hole. We defined these nice slices. They kind of went into the black hole. And then, so for example, our black hole is formed by collapse, like this. And our nice slices, they are always weakly curved. They stay away from all the curvature regions. And then they go back, hit the origin in some place before the black hole collapsed. And we talked about the splitting of modes inside and outside of the black hole, right? This is what we talk about when we talk about these subregions. We're talking about collecting radiation outside, and there's an inside, and we talk about the entanglement between inside and outside. But at the end of the day, we're working in GR. And this kind of splitting between inside and outside is not diff invariant. So really, what do we mean when we talk about the Hilbert space inside and outside? When we do a diffeomorphism that can mix our Cauchy slice. So have we really been careful in defining things in a diff invariant way? Subregions in GR are ill-defined anyway. How do you do the splitting? How do you define the splitting in a diff invariant way? Similar to this discussion that we've been having about, Maxwell theory or Yang-Mills. It's very difficult. A lot of subtlety crops up when you start to think about the constraints. Okay, so two things that we just mentioned. One is when we talk about entanglement entropy, it's really a UV divergent quantity. And when I draw a plot like this, maybe it's meaningless because it's all infinite. So, have I really precisely defined the problem if everything is infinite at the outset? And second of all, well, what is the inside? What is the outside? Are these diff invariant quantities? Have I taken the constraints into account? Have I actually been careful about defining all of these things? So we need to be more careful. Still need to be more careful, and we need to work in a setup where these issues don't arise, right? We need to work in a setup where we don't have to. Well, where at least we can control the UV divergences, we can make sure that we've done things carefully, and where the diffeomorphisms don't in the end hurt us, right? Because we're not exactly sure if we're computing the correct thing, right? So after the break, I'm going to set up this problem in a toy model in ADS-CFT. If you don't know anything about ADS-CFT, it's okay. And I'm gonna try to take it slow. But in the toy model that I'm gonna set up, we can control these issues: the UV divergences, the diffs, all of that. Okay. So I guess now's a good time, even though it's 5 minutes before the end. By a show of hands, who here feels like they know or feel comfortable with the ADS-CFT correspondence? More than expected. Okay, that's roughly 55% of you. Have seen it before. Have understand the basics of the duality.
Able to rederive it or just no?
No. Able to rederive it. There's no derivation. There's no derivation. There's just a bunch of checks.
So it's not like, wait, it's not approving duality to the conjecture.
If it were proven, it would be it would be a lot less useful, I think. If you could prove it, then you would be able to solve everything in the gravity side. It wouldn't be useful then. No, there's no proof. There's no proof. If you can prove it, then you would be famous, rich and famous. Rich and famous. Emphasis on the rich. I don't know if you would get the Nobel Prize, because nowadays there's always been this like experimental side to it. Fields medal if you're under 40. I only have 2 years left. So I'm like rushing. Hope. Yeah. But maybe like Andrew Wiles, maybe I'll get a special. I'll become one of those crackpots that all of a sudden starts working on the Riemann hypothesis in my old age. Okay, so the BHIP in ADS CFT. Okay, so so roughly you guys have heard this idea that quantum gravity in asymptotically anti-de Sitter space is dual to some conformal field theory. So the nice thing about this equality, which I'm not going to prove because there's no proof, is that some conformal field theory, emphasis on some because, you don't know for any asymptotically anti-de Sitter theory what the some conformal field theory is. We have some idea of some examples. But the important thing is that conformal field theory is also a Lorentz invariant quantum field theory. And conformal field theory, therefore, also has the area divergence in the entanglement entropy. Right? We just said any local quantum field theory with local operators has a ground state which is cyclic, and the cyclicity of the ground state means that it's super entangled. In fact, so entangled that if I restrict to any subregion, the entanglement entropy with the rest of my system is UV divergent. And that you can show in any Lorentzian variant quantum field theory with local operators. That's the content of this proof. Therefore, it also holds in conformal field theory. Conformal field theory is just a specific example of that more general statement. Okay? So let me draw that. So I have my CFT. I have my subregion. And the entanglement entropy, so R, I'm going to call this R. The entanglement entropy of the region R is A of R over some UV cutoff squared. It's the same as before. Okay. Now, in ADS CFT, we should be able to reproduce this area law divergence in the dual ADS space. So, just I want to remind you of how things are set up. What does it mean to be asymptotically ADS? Well, that means that I have a space-time, and in my space-time, I have a boundary condition. So my fields behave in a particular way, specified by a boundary condition. So anti-de Sitter space, we think about the Einstein-Hilbert action, which we wrote before, R minus 2 lambda. R is the Ricci scalar. Here we have a cosmological constant. And we're going to take lambda less than 0. That's what you mean, what it means to have anti-de Sitter space. And for this to be a well-posed initial boundary value problem, then you have to specify boundary conditions. So the way that people do that is that they draw some kind of Penrose diagram. They define Cauchy data here. So this is conformal compactification, just like we do for Penrose diagrams. And if you want to evolve this with these equations, then you have to specify particular conditions in the asymptotic region. So you have to specify boundary conditions. For example, what is the conformal class of the metric out at infinity? And these boundary conditions are what makes this spacetime asymptotically ADS. So you specify the boundary conditions, specify the initial conditions, and then you fill in by solving the equations. Okay? So that is to say that the structure of the spacetime at infinity is fixed. It's not like the case in flat space. In ADS, the spacetime is rigid at infinity. Diffeomorphisms have to die off at infinity. So while we have this issue with diffeomorphisms in a regular spacetime like flat space, and the splitting of regions is ill-defined when we think of a Cauchy slice, at least in ADS we have a region where we have boundary conditions and we have a rigid notion of the boundary. Yeah. Yeah, defining boundary condition at some space, some region in space, in flat space or de Sitter, is, I think, not fully solved problem. If you want, Chao Korn has worked on this.
show up into the boundary and specify that.
No. There's no, so in DS there's no boundary. So you have to, if you want to specify a boundary condition somewhere, you have to cut the space somehow. That's usually very violent. So it's usually not a consistent thing to do. So people are interested in that problem. Like say I did cut up a part of de Sitter or a part of flat space, and I want to specify boundary conditions. What are the consistent boundary conditions? That in Lorentzian signature, I think, is a not completely solved problem. I don't know. You can tell me, Chowkorn. Is it solved or not solved? Not solved. Not solved problem. So if you want to work on it, go for it. This area law divergence could be reproduced in ADS by considering, so now imagine that this is the boundary and this is ADS. They imagined what happens if you put a minimal surface into ADS. I'm going to call this gamma. And I just compute this minimal surface, the area of this minimal surface in an asymptotically ADS spacetime. And in ADS, the boundary conditions that you impose make it so that the volume grows at infinity. Spatial volumes are growing at infinity. So any surface like this in ADS would have diverging area if it actually went all the way out to infinity. So you have to cut it off to make this calculation tractable. You have to stop. Let's call this epsilon UV, some length scale, where you cut off the problem. And they observed that if you just do this, this is equal to the area of this minimal surface divided by 4G. So you could get the exact CFT, the leading divergence of the CFT entanglement entropy by calculating the area of some minimal surface appropriately cut off and dividing by 4G. And this kind of revolutionized the way that people started computing entanglement entropy. If you look at the papers from that time, you'll see that there are something like 1,000, 2,000 papers where people were just taking their favorite, geometry in ADS, add some matter fields, add some nonlinear deformations, whatever, and then computing areas, and then say, we computed some interesting CFT entanglement entropy. So, and people were hoping that they might see stuff like that in the lab. But the important thing is that this relates an entanglement entropy in quantum field theory, say on the boundary, to just an area of a surface. And so this starts to, begins to tie in with the information paradox, right? Because we have some area of some surface inside of the bulk. We ascribe some entropy to it. Okay, so when we do that for a black hole, that entropy is finite. Here we're computing some quantum field theory entropy, but we're still relating it to some area, some surface. So maybe we can use this to set up a problem similar to the black hole information paradox, but that is more in line with all of the things and is purely formulated within the field theory. So maybe this will answer your question about what are the universality classes. Okay, so what we're going to try and do is we're going to try and set up a page curve problem, but in terms of entanglements only on the boundary. Okay? And we're going to try and see if somehow in this toy model of the black hole information paradox, we might be able to see this page curve type behavior. Okay? Is that clear? All right. So this is the background. So this formula, this Ryutake Yanagi formula, I want to say another thing about it before I go into the setup. So this formula is proven. Now, you might say, well, how is it proven? There's no ADS-C proof. How can I prove this formula, right? Like, what does it mean? Okay, so I need to tell you one more thing about entanglement entropy. Just want to remind you about entanglement entropy. And the things that I'm going to say are gonna go back to the first lesson of LonTI about path integrals. I kind of reminded you guys about how path integrals work. It's going to come full circle, so I didn't like just say that stuff so that it can be forgotten. But if you don't remember anything in particular, feel free to stop. Okay. So the main point is that you remember that the entanglement entropy of some subsystem is obtained. First, you take some pure state, for example, do some splitting, and form the density matrix for the subsystem by tracing out the rest of the system. And then you compute something like trace of rho log of rho minus. We reviewed this last time. Okay, so you have some subsystem, you have a density matrix in the subsystem, and then to compute the entanglement entropy of that subsystem, you compute this trace rho log rho. Now, part of the issue is that computing a log is very difficult in general of some big state. You have to find its eigenvalues, then take it to the log because this is the log of a matrix. This is a hard thing to compute. So people try to do it in a different way. So instead, you do something called the replica trick. So what you do is first you compute trace of rho to the n. And trace of rho to the n is much easier to compute than rho log rho, right? Because you just square a matrix and then you compute its trace. And you compute it for a sequence of n. And then the idea is that you try to derive an analytic function that matches trace rho to the n for all of these integer n's. And then you say, so then you have S Renyi, this is called the Renyi entropies, as a function of n. And then at the end, what you take this function as a function, can you guys read this? Okay. What you do is that you say that the entanglement entropy, there are many different ways to do this, but one is, for example, take 1 minus n dn of log S Renyi of n at n equals to 1. So once you have this formula, you just take its log. You're not taking the log of a matrix anymore. You're taking the log of a number. You compute some derivatives, and then you're done. So so what people do is, in order to compute the entanglement entropies, they first compute these Renyis, and then they use this trick to relate it to the entanglement entropy. Okay, and the way that this formula is proven is by doing this trick in the path integral of gravity. So instead of computing some entanglement entropy of the state, you imagine replicating the state n times, fixing boundary conditions on some surface, and then trying to extrapolate how this thing behaves, how its derivative behaves at n equals to 1. So the way that it works is that you take the quantum gravity path integral. So what people do is they imagine that, so they imagine that this is the boundary, and then you have some bulk associated with it, and then you stitch it up to a bunch of different copies of the boundary. And then you fill in. And then to define your Ryutake-Yanagi surface, you impose some boundary conditions that fix the field configuration on your region R. And then you have to do that in all of these copies. So then you have some copied quantum gravity path integral with some Zn symmetry. And then this extremal surface kind of appears when you try to understand this limit as you take n to 1. It's some fixed point of the discrete n rotation symmetry.
Only when you kind of trace it up with S1.
Yeah. I'm not drawing it. I'm not drawing it. Yeah, there's a lot of stuff suppressed in this picture. This picture is only supposed to be schematic. If you want to see this this proof, it's in a paper by Lefkowitz. I should know how to spell this. And Mollison. You require smooth geometries in the bulk. But this extremal surface arises as a fixed point of this path integral. It's like a fixed surface of this Zn symmetry in the limit as n goes to 1. So this is the statement that it's proven, that this that we can understand this from a Euclidean path integral perspective by fixing some boundary conditions on the boundary, filling it in, considering this replicated path integral as a function. Okay. Now, I want to also remind you that so another point that I need to bring up is that in ADS, the page curve looks different. Can anybody tell me why? Does anybody remember anything about black holes and ADS? You? Large black hole. You can, yeah. No, you can in ADS, it's fine. Huh? It doesn't evaporate. Yeah, so what is the entropy of a black hole that doesn't evaporate? Constant. So this is the S black hole, and this is the S of the radiation. So the page curve in ADS looks like this. Solving the information paradox in ADS would be finding a calculation that lets you reproduce a curve like this. Remember, up to UV divergence. Okay. So now our goal is to reproduce a curve like this in ADS. using this Ryu-Takayanagi formula and the Euclidean path integral, because the Ryu-Takayanagi formula really is related to the Euclidean path. Very. Okay, so how do we do that? Okay, so we want a setup where we prepare a black hole, right? It has constant entropy, and we start collecting radiation outside of the black hole. And we want to see that the entanglement entropy of this radiation will grow for a bit, and then all of a sudden saturate. That's the setup that we want to prepare. Okay, so now I need to remind you how to prepare a black hole in ADS-CFT. Okay, so so let me draw the Penrose diagram of a black hole in ADS. Black hole in ADS has a Penrose diagram that looks like this. And this is an eternal black hole. So it's very much, so in flat space, this thing looks the same. It's like, you might have seen it. In flat space, it looks like this. And the fact that we have asymptotically ADS data is just the statement that our Penrose diagram looks like this. You have time-like vectors at spatial infinity, because you can still have time translations along the boundary. And there's a very famous setup where the so will be very similar to the calculation that you did in Rindler. So remember, in Rindler, what we did was we thought about the Cauchy slice, and we asked what was the state of an observer outside of the Rindler horizon. So here, in ADS, you have a very similar setup. You have some Cauchy slice, and you're asking what is the state observed by somebody outside of, for example, the black hole on the right side. It's a similar question for somebody standing on the black hole on the left side. Okay. And what we found in Rindler was that in Rindler space, the state on the right side was, well, the entire state. Let's go back to so the vacuum. So in Rindler, we wrote that the vacuum O Minkowski was some entangled state between populated left and right guys, sum over I, and then e to the minus beta, I think, over 2 e and I. So we didn't write it in this way, but this is essentially what we wrote down. You go back to your notes. And if you look at this, you see the structure is that of an entangled state between the right and the left, right? So it shouldn't surprise you that the state O ADS is exactly the same. I'm going to write it like this. Yeah. But the important thing to note is that in ADS, this is a state of some CFT, which we call the CFT living at the boundary of the right side. And this, maybe I'll call this CFT right. And this is some state in the CFT on the left. Are you guys okay with that?
Really naive question. When you say this left and right, that some region, virtual boundary region separates in the geometry.
Yeah, they're completely separate. They're space-like separated in the geometry. They live at the two boundaries.
In which sense they are separate?
I mean, the only thing that connects them is the interior geometry, but they're space-like separated. You can't send a signal from one to the other. You'll hit the singularity in the geometry.
So this is for the CFT set picture of the ADS picture.
So this is from the ADS picture. In the CFT picture, you just prepare a thermal field double of two CFTs. So this is often called the thermo field double. Because you take... Yeah, very good. So this is religion. This is the belief that anything in the bulk can be rephrased as something in the boundary. So we derive this just in the Rindler picture. We derive this kind of entanglement. And now the statement is that, well, it must be that I have a state in my dual CFT on the right and a state in my dual CFT on the left. And this is the structure of that state. Prepare my state this way. Okay?
Sorry, and what's the mathematical definition of that?
No, there's no definition. I just have a CFT, I double it, and then I consider energy eigenstates, and then I prepare this state. This is the thermal field double.
I think of this, we have the religion of this like healthy isomorphism for pretty much one bulk for the space to the CFT of the space. That's what we use. Right?
Yeah. There's a map from the bulk Hilbert space to the CFT. Exactly.
What's the importance of Rindler?
The importance is that I did this example a few lessons ago, so I'm using it so that they see the relation. Any other questions? Okay.
When you write down the vacuum phase in A, that means the vacuum phase.
Yeah. So this is this is the like vacuum on this Cauchy slice in the effective theory, in the effective bulk theory. Yeah, but there should be a mapping to the boundary theories. Okay.
So here you think relate to the thermal field double in the sense you prepare the
Correct.
state with like you can also do one more state.
Yeah, you could. I mean, for single particle excitations on top, you can do it too. But I mean, not all states have an easy geometric interpretation. But black holes are nice because we can, when you have a horizon, the local entanglement structure kind of fixes everything for you. You get that from the Rindler calculation. There are some people who claim that those are related to some kind of multi-boundary wormholes, but they're not very simple geometries to write down, especially in Lorentzian. At least these ones have nice Lorentzian pictures. Okay, so this thing is a thermal field double. Okay, this is what we call the thermal field double. So now I'm going to draw a picture for you. Wow, I'm kind of running out of time. I'm going to draw a picture for you for how we derive, how we prepare the thermal field double using the Euclidean path input. Okay. So I want you to remember that there was this idea that if I want to compute some path integral in Euclidean signature at finite temperatures, E of beta, I just compute the path integral with periodic boundary conditions. You guys remember that? We reviewed that in the first lecture. Okay. Now, this is a partition function. Partition function is a number. It's not a state, right? Partition function is just a number. But you can think about it like the norm of some state, that number. And the way to think about that is to actually cut this path integral open. And then you have something that looks like this. And you have state 1. I'm going to call this maybe E left, E right. Some state of the theory. And if this cut state will have a norm that's equal to Z of beta, it must be that this cut state is equal to the thermal field double. Because if you sandwich it together, you'll get sum over e to the minus beta e. So the way that people draw the preparation of this thermal field double is to first imagine the path integral that gives you the thermal state with periodic boundary conditions, cut it open. And then you'd have a system defined on 2 Cauchy slices. And that system defined on 2 Cauchy slices is the entangled thermal field double state. So is this picture, the intent of this picture roughly clear? I can't derive it for you right now because there's not enough time. We only have about 20 minutes left. And then what people usually do is they imagine time evolving this state. So you start in Euclidean, and then now you have a state that you can evolve in time. So this is, this part we would write as Euclidean evolution. And this part we would call Lorentzian evolution. So this is like T going up. Okay? So this is how we can prepare, using the Euclidean path integral, how we can prepare such a state, such a thermal state, a state that would be dual to a eternal black hole. Okay? One way to think about this in ADS-CFT is to think about that this is the Euclidean path integral for the boundary theory. I do half a rotation in Euclidean time, and then I evolve in Lorentzian time. And then the bulk is filled in between these 2 sheets of paper. And the bulk gets filled in with a black hole. So there will be a black hole in between these 2 sheets of paper. So somewhere in here, there will be some black hole, and it evolves in time. Okay? And it might be some extended black hole or something like that. So from the perspective of filling in this folded sheet of paper, so you have something like this. You fold it. This is my boundary path integral. And then the thing that fills in over here is the gravity path integral. The gravity path integral will have a black hole in between these 2. A black hole horizon that blocks communication from one side of the sheet of paper to the other side. Is that picture roughly clear? This picture is general. This picture is general. It's general, yeah. It's not just CFT2. Okay. But, yeah, everything I said is general so far.
So we can compute this CFT stuff without all the calculating.
This is all CFT. Yeah, if you want to, compare, then the bulk will have some, because you've prepared the thermal state, the bulk will be in some black hole scenario, okay? All right. So now we want to set up a page curve like calculation. And part of the problem is that we need to localize the black hole. So where are we going to collect the radiation, really? Like, we need to think about what subsystem. So we need to think about it from a boundary perspective now. You're now an experimenter who is using the dictionary to their fullest capability, and you want to try to set up as best you can a analogous experiment to doing to capturing radiation from an evaporating black hole, but just by phrasing it in the boundary. Okay. So in order to do that, I need to draw a few more pictures. So the dial was highly unconceptual today, because I'm not going to show you all the math. But if you trust me, then we'll get to the end of the course. Okay. So now we're going to take this setup, and we're going to imagine doubling it again. Okay? So I'm going to imagine that I have, so let's draw the Euclidean picture first. I'm going to prepare a thermal state of some CFT A. And then I'm going to, and this goes off to infinity on the left. Remember, this picture means I've prepared the partition function for CFT A. But then I'm going to cut CFT A at some point, and then I'm going to couple it at some interface to a CFT B at the same temperature. Right? Okay, so what's the Lorentzian picture? The Lorentzian picture of that is going to be the same as here, only times 2. So we have so here's my CFT A. Then here's my CFT B. And then I evolve in Lorentzian time. Now you might ask, why did I do that? So if you're paying attention, what kind of state will I have here? I have a thermal field double state, but now I have 4 different parts. I have right and left of CFT A, I have right and left of CFT B, and I have the interface. And inside of all of this, in this big sandwich, there's a black hole. Okay? There's a black hole filling in these two sheets of paper. Okay? And so this part is Lorentzian. So this is Lorentzian. And this is state preparation in Euclidean. I prepare this state in Euclidean, and then I evolve in Lorentzian. I do half a rotation with beta over 2, the particular temperature that I'm interested in. That's the temperature of the black hole that will fill in the bulk. Okay? Now, why did I do it this way? Why did I do this doubling? Why did I introduce an interface? In fact, these interfaces are kind of a subtle thing. In order to introduce an interface that preserves conformality of this theory, it's not so easy. But there are known conformal boundary conditions now in CFT2. So, it's less understood how to do it in higher dimensions, but it is believed that you can engineer conformal boundary conditions in higher dimensions. So, so if you want specifics, I can point you to specifics in CFT2 for how you might compute such a thing. You have to imagine that such a thing can be done in higher dimensions. But why did I do it this way? I did it this way because we want to imagine a scenario where my bulk picture looks something like this. So my bulk picture, by bulk picture, I mean what? I mean, I'm restricting to an observer on the right side. So they only have access to CFT-A and CFT-B on the right side. And then the interior of their geometry will have a black hole. Okay? So let me draw the boundary on their side. So here I have, here I have CFT-A. And here I have CFT-B. And I have an interface. The interface cuts across the bulk, some surface that cuts across the bulk. And there's a black hole in here. I'm going to draw that too. Okay, so why did I go through all of this? So I'm going through all of this because I want you to see that you can be careful about things, but you have to, be very honest with your calculations. So now, why did we do it this way? Well, you do it this way because if you look at this bulk picture, see that the interface falls into the black hole. There's a sense in which you can try and engineer things so that if you squint, the black hole lies on the interface. And you want to collect radiation in the interface subsystem. Actually, these conformal interfaces carry their own degrees of freedom. So they're not just like, if you had like purely passive boundary conditions, there would be no degrees of freedom at the interface, but you can engineer it such that this is some lower dimensional quantum system that has its own degrees of freedom and captures its own radiation as well. So we're going to be working in the approximation where this is also some quantum mechanical system with a large number of degrees of freedom. Okay, so the interface will be another quantum system where I can collect entropy. And now I have all of the ingredients to set up a page curve. Okay, so what do I want to do? So I want to compute the entanglement entropy of so what do I want to do? Right? I want to compute the entanglement entropy of this region, the interface region in my CFT. But it's doubled, right? It's doubled. So I have to also consider the other side. What is the entanglement entropy on the other side? Right? Let me draw that big. I'm going to blow that up. I mean, it's one dimension lower quantum system. To make it so that you have conformal boundary conditions and all that, it's not quite that it's not enough to say that it's a CFT. Yeah. Yes. I'm going to draw this big. Okay, so now you guys remember that I can compute this entanglement entropy using a Ryu-Takayanagi surface, right? Okay. So what is the statement? I want to find the minimal surface that obeys these boundary conditions. So at early times, the minimal surface actually stretches across the CFTs. So it goes from one side to the other. I don't know if this is clear in the picture. It goes like that. And if you compute those, they're obviously UV divergent quantities, but we can control the UV divergence. We know where the UV divergence is. It's just a piece that you can just calculate. Okay. So in that phase, there's a very large offset. Depends on how you regulate the length of this curve, but as a function of time, this thing grows linearly. Okay. And then at some point, it's no longer the minimal surface because it keeps growing without bound. And there's actually another minimal surface that appears, and it's the one that stays on one side and cuts across. So then it becomes like this. And those don't evolve in time, those entropies, because they are, the outside is time independent, and these lengths are time independent. The reason that this guy grows in time is because actually if you draw the Penrose diagram of ADS, you have surfaces that are going like this, going through the black hole, and inside of the black hole, there's space is growing in time. You have some cosmology, and that's causing this length to increase. But at late times, that's no longer the dominant contribution. The UV divergence is the same, so you can compare them. And at late times, you get another contribution, which goes like this. And the total curve is simply. But here, everything that we did was UV divergent. And so we can compare the UV divergence and regulate appropriately, and everything is fine. Okay. So is this the page curve? That's right. That's right. It's the question of, yeah, what is the dominant Ryu-Takeyanagi surface that calculates this entanglement entropy for the interface? And of course, like, there are details involved. Like, I haven't given you any information about this interface, so you can't go and do this calculation yourself. But I can point you to papers where if you work with minimal assumptions, you can go and calculate this, make some assumptions about the interface, how many degrees of freedom it has, etc. And you can see where this height lies. On the gravity side, this calculation is just a calculation of surfaces. But this calculation is capturing all of that. It's supposed to be calculating all of that. Because you've prepared yourself in the thermal field double. And the geometry is capturing this growth of entanglement. Okay. So I have -5 minutes left, but I want to say one last thing before the course is over. So here's an example. This was just to say, here's an example where you use ADS to try to formulate a version of the black hole information paradox phrased in terms of entanglement in a way where you think you can do the calculation in a reasonable way. Now, why is this not a resolution of the information paradox? Well, first of all, it requires ADS CFT. So it requires me to be able to make this by fiat jump that things that I compute in some bulk spacetime are reproduced using CFT calculations. And then I use calculations in the bulk to calculate the stuff in the CFT. There's like a whole mixing of all those things. But moreover, it doesn't tell us how the semi-classical picture broke down, how the effective field theory calculation in the bulk broke down. This gives me a perspective on how to compute things correctly, get a correct page curve. But it hasn't told me how I'm supposed to think of the state, the effective field theory state, changing in time. This doesn't answer that question. So I want to leave with some words that people say with regards to what's happening in the bulk effective theory. Like where is the bulk effective theory going wrong when you compute this entanglement entropy? Are there any questions about this? Was this okay? So the replicated CFTs is just a trick for preparing this state, this entangled state. Yeah. Oh, you mean this interface? So we did this in order to introduce this interface, and the reason I introduced an interface is to give you a place where you can imagine that the black hole lives. It lives in the whole space-time. That's right. But we want to pick a particular subsystem, which I called the interface, where we are going to collect the radiation. That's why I introduced this interface.
You mentioned this domain interface is not necessarily conformal.
Well, if you're not careful, but in this example, we're always we're restricting to conformal boundary conditions.
No, I think it's not CFT.
No, it is. It's just a boundary CFT or an interface CFT.
Oh, okay. So then we still have ADS CFT.
Yes. That's why we used ADS CFT rules. If we didn't have that, then it would be a problem. Okay. Any other questions? So what do people say? Oops. So the last thing I want to say is that people make this argument that something has to go wrong with the entanglement entropy calculation. So I want to remind you how we do the entanglement entropy calculation. Remember that one way to compute the entanglement entropy is to do this Rindler entropy trick. So we compute rho to the n instead of trace rho log rho. And first I want to remind you that in Euclidean, the black hole looked like this cigar. You guys remember that? We did that earlier in the course. There's this idea that if you take the Schwarzschild black hole and then you analytically continue to Euclidean time, you had to identify the calculation or the time coordinate. So the black hole looks like this. And then I'm going to draw this region over here, which is the extension of this cigar, where the radiation is going to live. Okay? And I'm going to draw it twice. Okay? Okay. So this is something that you would consider when you're computing trace of rho squared, right? And I want to highlight the state of the radiation. So, for example, you might have radiation here in state I, radiation here in state J, and then if you're going to compute trace of rho squared, you'll have to have trace the radiation here in state J. It's like related to here, and then on the other side I. That's trace of rho squared in pictures. So, so the claim nowadays is that when you're computing the entanglement entropy using the Rindler entropy trick, this is the type of geometry that you would consider if you are not being careful with the calculation. It's the dominant contribution at early times, but the statement that people make is that when the page curve switches back, this is not the correct calculation. This is not the correct semi-classical picture to be using when you're computing the Rindler entropy at late times. People say that really at late times, so this is early times, early time picture. People say that at late times, really, you should consider the following. We have, again, radiation state I. On the other side, state J. J. I. But in Euclidean, there are also geometries that look like this. When you're computing rho squared. When you're computing just one geometry, trace rho log rho, you wouldn't necessarily think that such connected geometry should exist. But if you're using the replica trick, first computing trace rho squared, there will be contributions like this. And the claim nowadays is that Hawking neglected to compute the contribution of these guys. And these are the guys that'll bring the page curve down when you continue to n equals 1 again. What that means for the Lorentzian picture, I have no idea. But that's the words people say. So now you're caught up. So get cracking on figuring this stuff out.